Hello again. Today and next time actually I'm going to talk about heat transfer. It's a very important topic. We're going to begin with just clarifying some words to make sure we know the difference in some words. First word is heat. So when we say heat transfer, what do we mean? So heat is energy transferred due to a temperature difference. So when we talk about heat transfer, we're really talking about transfer of energy, heat, and we're always talking about transfer of energy. That's because there's a temperature difference between two locations or two objects or two ends of an object, something like that. Now, that begs the question of what is temperature? So temperature is a measure of the average kinetic energy of molecules. So if the molecules are moving really fast, on average, some might be moving really, really fast and some not so much, but if on average they're moving really fast, it means you have a very high temperature. If they're not moving so very fast, you have a low temperature. Notice it's a measure of average kinetic energy. It's not an energy. It doesn't have units of energy. So please don't say it's an energy. It's a measure of that. It has different units, but if you know one, you know the other. Now, then there's another word used in thermal physics called internal energy that is sometimes confused with these, and I just want to clarify what it means. It is the total energy of all the molecules of a system. So internal energy means you add up all the energies of all the molecules. So if you double the size of the system, you actually double the internal energy, whereas you wouldn't be changing the temperature because that's a measure of average kinetic energy. And heat is energy being transferred. Although sometimes often engineers will use this term more loosely, so please don't be upset if they do or even if I do. Now, a couple of units that you'll run into in everyday life that you should be aware of. There's something called the calorie. That has a historical definition that helps you understand what it means and has a more formal definition. Let me check something. Just making sure I had the video going. So calorie historically was the energy to raise 1 gram of water 1 degree Celsius. To raise the temperature of 1 gram of water 1 degree Celsius. Now we define it instead rigorously in terms of the joule. 1 calorie is 4.186 joules. But it's hard to get any intuition, for me at least, it's hard to get any intuition from this. Though from this I get a certain amount of intuition. I know what a gram of water is, the energy to heat that by a degree Celsius. I can sort of think about that. So that's the calorie. By the way, the calories in your food, when you eat a candy bar, there are actually 1,000 of these. Those calories are actually a kilocalorie. Now, another unit you'll run into in everyday life is the BTU. So if you buy an air conditioner or a heater or something, this is the British thermal unit. And this historically is the energy to raise the temperature of a pound of water 1 degree Fahrenheit. Energy to raise the temperature of 1 pound of water 1 degree Fahrenheit. I just think you ought to know those because you run into them in everyday life. So you go buy an air conditioner, it might be a 12,000 BTU air conditioner. What is that unit, BTU? But it's telling you that energy. Now, all right, so those are just some definitions. So I said I'd talk about heat transfer. And specifically, I'm going to talk about the rate of heat transfer. What does it depend on, and can we calculate it? We're talking about 3 types of heat transfer, 2 today, 1 next time. First is conduction. Excuse me, sorry. Conduction is heat transfer by molecular collisions. So suppose I have a block of material here, maybe it's steel. And I start heating up one end of it. Perhaps I have a torch. And so I have, flame coming out this end. So I'm heating this end. The molecules inside this end of this block of steel will start vibrating faster. So they'll start vibrating really fast, and they'll hit the molecules beside them. And those fast-moving molecules will hit the molecules beside them, and all of these collisions, these molecules hit them, these molecules hit them, these molecules hit them, these molecules hit them, these molecules, and those collisions increase the vibrations of the molecules all through the steel. Now finally the vibrations over here can vibrate the air around the steel or the water or whatever's over here. And so what you have is these collisions of the molecules move the energy through the steel. That's conduction. That's heat transfer by conduction. Notice the molecules stayed where they were. This molecule stays where it was and just moves, just vibrates, just has collisions, but it doesn't move over here. That'll be important later. Stays where it is and just has collisions, and the collisions transfer the energy. Now, can we calculate how the rate at which that energy is transferred? Well, what does it depend on? It depends on the temperature difference. The higher the temperature over here, the faster the rate energy passes through this block of steel. So the greater the temperature difference, the greater the rate. So what we want to know is the power transfer. Power, that's Q over T, where Q is the energy being transferred. And so we expect it to depend on T2 minus T1, the temperature difference between the two sides. We think it should depend inversely on this distance, D. That is, the thicker this is, the longer it takes for energy to be transferred, the slower the rate. If this were a very thin plate of steel, the energy would get through it very rapidly. As it gets thicker and thicker, energy gets through it less rapidly. So that means I put the D in the denominator. Might be less obvious, but the area of the plate is important. Area. The bigger the plate, the more rapid energy gets through it. Well, you might picture that if we were calculating the heat transfer through a window, heat loss through a window on a cold night. The bigger the window, the more rapidly you would lose heat. So this area is something the heat loss depends on, and the bigger the area, the more rapid your heat transfer is. And finally, the heat transfer depends on the material. So we put a constant here, K, that depends on whether this is steel or wood or silver or peanut butter or whatever this is made of. There's a material dependence. And this is called the thermal conductivity. It's something you measure or look up in a table. It tells you the material dependence. So for example, K for glass, I looked up, is 0.84 joules per second meter degree Celsius. And joule per second is a watt, so this could also be written as watt per meter degree Celsius. You might see it either way. Now, I'm going to do an example of doing this calculation in just a moment. But let me do a quick aside as well, just because of something you'll see in everyday life. So just an aside. There's something called R factor. So you'll see this at Lowe's or Home Depot or somewhere like that. R factor is the ratio of D over K. And this tells you how insulating a material is. The bigger the R factor, the harder it is for heat to get through it. So as D gets big, this power loss gets small. As K gets small, this power loss gets small. So R factor is a measure of how insulating a material is. So for example, if you buy insulation, it might be expressed as an R11 or an R13, or when you buy a home, your home might be spec'd to have R30 insulation in the attic. And that insulation is telling you what is this ratio. It has interesting units of feet squared, degree Fahrenheit, hour per BTU. So again, it's how insulating your insulation your insulation is. And so that's something you just will run into in everyday life. All right, so let's do an example of this. So what I'm going to do is calculate the rate of heat loss through the sides of a teacup. So here is a teacup, and I'm letting it be 8 centimeters high, average radius of 4 centimeters, a wall thickness of 1 centimeter. Let it be made of glass. I'm going to let the tea inside have a temperature of 70 degrees Celsius. At 100 it'd be boiling roughly, and I'm going to let the tea outside, the temperature outside be 20 degrees Celsius, sort of a room temperature. I'm going to calculate the heat loss through the sides. Now there'll be other heat loss. There'll be heat loss out the top, there'll be heat loss out the bottom, heat loss for other reasons. I'm just calculating the heat loss through the sides. So that means I need to know K, A, delta T, and D. The T's we know, 70 degrees C and 20 degrees C. D we know is this 1 centimeter. We need K, I looked up, is K for glass, is that 0.84 watts per meter degree Celsius. The only slightly difficult thing is A. What is A? A is the area the heat is being transferred through. So A is the area of the cylinder the heat is flowing through. So the average A is a cylinder of radius 4 centimeters and height 8 centimeters. So A is 2 pi RL, circumference times height, 2 pi times 0.04 meters times 0.08 meters. So that turns out to be 0.020 square meters. So now we know everything that goes in here. K is make that a little tidier, 0.84 watts per meter degree Celsius. A is 0.020 square meters. Delta T is 70 degrees C minus 20 degrees C. And the thickness the heat is being transferred through is the 1 centimeters, 0.01 meter. So this will give me my power loss through the sides of the cup. It turns out to be 84 watts. So pretty straightforward. So that's heat transfer by conduction. I calculated a heat loss. It could have been a heat gain. It could have been heating something, and that's conduction. Again, it's by molecular collisions. Now the next type of heat transfer we'll talk about is not conduction, it's convection. Very similar sounding words, so we have to be very careful. This is heat transfer by convection. This is heat transfer by movement of mass. So now the mass is moving from one location to the other. For conduction, I emphasized it was not. So a couple of ways this can happen. Suppose I have a pot of water and I heat the bottom of the pot somehow. On a burner or a stove, maybe with a candle for some arcane reason. And so the water here in the middle will get less dense and it will start rising. And this will set up these currents in the pot. So these currents will start flowing. So the hot water actually rose and displaced the cooler water, and the cooler water flows in and starts warming. So these are called convection currents. Notice the mass itself is moving from one place to another. That's what makes it convection. Another way this could happen is you could have a source of heat, say some sort of old-fashioned radiator here. I hope you know what that means. So it heats up the air, and we put a fan over it. So this is supposed to be a fan, and the fan blows the hot air from one location to the other. Hot air, and the air actually moves across the room. This is called forced convection. When you, of course, forced it by putting a fan on it. That's what typically happens in your heating system in your home when you have a blower on it that blows the warm air through your house. So, but notice again, the hot air was here and it moved over to there. That's what makes this convection. Let me do an example of it. There's no one equation that deals with convection. It just depends on how the mass got from one location to the other. When the fan blew it, it's very different than when you have the current in the water pot. The Gulf Stream in the ocean moves warm water from one location to another on the planet. So there's no one equation that takes care of this. You just have to think through and model the best you can that particular situation. Now, my example is air exchange in a room. Could be this room, for example, that I'm standing in. So maybe you have the air in a room is being taken out of the room, passed through a heater, and brought back in the room to be warmed a little bit, just because it's winter and you need periodically to warm that air. So here's a room that's 3 meters high, 8 meters wide, by 10 meters long. That's a big room. Anyway, so suppose every 30 minutes you need to take all of the air in that room and pass it through a heater and warm it by 10 degrees. So every 30 minutes need to pass all the air through a heater and warm by 10 degrees Celsius. How much power do we need to do that? Well, the power would be Q over T. Q to just warm a volume of something we've learned to do, that's MC delta T over the time to get power. So we know delta T is 10 degrees. We're warming air, so we look up the specific heat of air. We need to know the mass of the air. But we know that density is mass over volume. So mass is density times volume. And we know the volume is 3 times 8 times 10. I looked up the density of air. Now the density of air is not a fixed number. It depends on how much moisture is in the air. So I looked up a typical value. So this will be 1.225 kilograms per cubic meter times 3 times 8 times 10, 3 meters times 8 meters times 10 meters. And that tells me the mass of air is 58.8 kilograms. I don't really have that many significant digits, but humor me, let's pretend I do. So this is 58.8 kilograms of air. Specific heat of air, I looked up. That's, again, that depends on how much moisture is in it, but 721 joules per kilogram degree Celsius. So be sure you make a note that I got that from a table, because it's just going to appear in your notes. The temperature difference is 10 degrees C. The time is 30 minutes. So 30 minutes times 60 seconds per minute to get our proper units. And that turns out to be 236 watts. So about, 200, 250 watts, something like that. Is that a plausible number? Yes. I mean, how much energy would it take to keep a room warm? That's like the smallest setting on a small heater. If I'd gotten 2 watts, I'd think, that's probably too small, probably there's something wrong. If I'd gotten, 20,000 watts, that's clearly too big. So this is a plausible number for keeping a room warm. All right. So, and there'll be other types of heat loss. If the room has windows, there'll be heat loss through the window. There may be heat gain from other rooms, from people in the room. There'll be heat gain due to that. So it could be a complicated situation. This is one component of heat transfer to a room. All right, so that's all for today. And next time we'll talk about heat transfer due to radiation. Cheers.